Hello everyone, my name is Payman. I study the scanning magnetic field response with respect to radiation of magnetic field for paramagnetic material, in which the spin spin coupling is here. So let's begin with some principles here. The response of material to an external magnetic field contributes to magnetization. There are different types of material with respect to magnetization. One of them is paramagnetic materials. And in paramagnetic materials, we can see weak induced magnetization in the magnetic field. The important factor is susceptibility, which magnetic susceptibility is a measure of how much of the material will become magnetized in an applied magnetic field. So for paramagnetic materials, we have a Court's law. In many paramagnetic materials, regarding to the Court's law, magnetization is proportional to an applied magnetic field, which is shown by a linear function here. M is magnitude of the resulting magnetization, and H is magnitude of the applied magnetic field. And susceptibility is also a function of temperature in a fixed magnetic field. Magnetic susceptibility is proportional to the temperature, which is a hyperbola function. Which means if temperature is lower, the magnetization increases. We simulate the lattice of ruthenium chloride in MATLAB. Our assumption, or basic assumption, is that in a honeycomb lattice of ruthenium chloride, we choose two atoms in the honeycomb lattice, and we distribute we consider those atoms as a canonical ensemble with random distribution of nucleus spin. And in each simulation, the temperature is considered as a fixed value. So here is my results. In the left-hand side picture, we can see the magnetization with respect to the magnetic field for different temperatures. The left figure shows the change of magnetization in respect to magnitude. The slope of the line in low magnetic fields is calculated for each temperature. Magnetization for the small magnetic field is proportional to the magnetic field, as I said before in the last two slides, which is consistent to the Court's law. The right-hand side figure shows the calculated susceptibility, which fits nicely in the hyperbola function. And as you see, the results are consistent with the Court's law. In this figure, we can see the effect of magnetic field on the susceptibility. As it's seen, when the temperature increases, the minimum of the plot is shifted toward higher magnetic fields. In low magnetic fields, it is seen that the susceptibility is proportional to the magnetic field. And I calculated the slope for each temperature. Also, by increasing the temperature, the slope increases. Meanwhile, in higher temperatures, the minimum of the plot is shifted to large magnetic fields. Regarding to the Court's law, susceptibility is inversely proportional to the temperature, and susceptibility in this figure, as you see, susceptibility begins from 0 and then decreases to a minimum value, which almost the same for all temperatures, and then increases to the 0 and stays constant. In this figure, I plotted the average energy with respect to the magnetic field. Regarding to the figures, the average energy with respect to change of magnetic field are similar for all cases in the higher magnetic fields, except for the low magnitudes. The external point of flood in starting region is shifted toward high values of magnetic field by increasing temperature. In high values of magnetic field, the curve converges to a line, and as you see, the slope of the line for all the plots are similar, and it shows it kind of does not depend on the temperature. Average energy of the system, so we can conclude that the average energy of the system does not depend on the magnetic field. It does not depend on the temperature in high magnetic fields. Beyond the threshold value, the relation of average energy to magnetic field is nonlinear for in a starting region in the low magnetic fields. However, for large magnetic fields, average energy is proportional to the magnitude, and there is a linear relation. In the last plot, in the last figure, I plotted the derivation of the energy to the magnetic field. As you see, after a threshold value, the derivative of energy stays constant, which means energy is linearly dependent on the magnetic field in large magnitudes. The minimum point of the plot is shifted toward larger magnetic fields by increasing the temperature. In low values of magnetic field, it is seen that the slope of the plot decreases in higher temperature. So as conclusion, magnetization of a paramagnetic material is proportional to an applied magnetic field for low magnitudes. The slope of magnetization with respect to magnetic field decreases by increasing temperature. Therefore, magnetization is in a paramagnetic material is inversely proportional to the temperature. Also, relation of susceptibility and applied magnetic field is almost linear in low magnitudes. And the last conclusion, average energy of the system has linear relation to magnetic fields in large magnitudes. These are my references, and thank you for your listening.
Thank you, Payman, for presenting, and paper is open for discussion. Anyone in class? Anyone online? Let me offer something for the discussion. Would you please go to forward? Yeah, here. So I do not have exact formulation, but please comment or confirm that as magnetic field increases, magnetization increases as well, goes from 0 to whatever negative value. And you can use your microphone probably. No.
So you mean I should explain?
Just confirm if verbally how magnetization changes with increase of magnetic field.
Okay. So as you see, I calculated. Thank you. I calculated the slope of each figure for each temperature. And in the starting point, which means in a low magnetic field, the relation of magnetization and the change of magnetic field is linear. So I calculate the slope, which means, and the slope of the magnetization with respect to magnetic field is susceptibility. So the amount of this slope is equal to susceptibility. And then I plotted the susceptibility with respect to temperature. And these 4 points are my data. The curve is the theta function for all of these 4 points. And actually I should have put the equation for this plot in Excel, but I don't know why I cannot do that. But the regression that I got was to power 0.95, which is kind of close to the negative one. And we know based on the Corey's law here, we know that the suspectability is the function of temperature to the power negative one. So my results are consistent with the Corey's law.
Okay, but here is the actual question. And it is question both to Damon and to everyone in the class. Please, we will be done very quickly, very soon, but please try to concentrate and think actively. In which situation magnetization as function of magnetic field will be zero, will not change? What should we do so that magnetization will not change as we increase magnetic field?
So based on this, what I guess in 5 magnetic fields, it does not depend on the magnetization does not depend on the magnetic field. And also by increasing the temperature, you can see that threshold value increases.
Okay, yeah, thank you very much. You told everything correct, but it is a preparation to be attentive to the next talk. Any other ideas or suggestions for if you want to echo? Just share.
If magnitude of magnetization is the same in an increasing supply, we would also need to increase temperature, as according to Newman's paper in equations 1 and 2. We can derive that the magnitude of magnetization M is equal to C, the constant over temperature times B. So if B is increased, we will need to increase B by some other proportion.
Thank you, Stephen. And I would like everyone to start paying attention to the talks, the last but not least talk that will be following, which are other conditions that no one of us mentioned for magnetic field not changing magnetization. So it will be quite surprising and unusual. So, any more questions to Payman online or in class? If no, please join me thanking him once again. Thank you, Payman, and everyone is Payman person is welcome to stop sharing. And the next presenter is Tyler. Okay, I see you are sharing.